Hello, Universe Explorers, and welcome back to NK Fantastic. I'm your host, and this is the channel where we take the cosmos, shake it up, and see what fantastic facts fall out. You know, we humans like things to make sense. We like neat boxes. We like rules. We like it when A plus B equals C. But then, we look up. We look up at the night sky, and the universe just laughs at our neat little boxes. The universe is a place of profound, mind-bending, wait what, contradictions. It's a place where the heaviest things are invisible, where time itself can be stretched like taffy, and where the entire cosmos is expanding, but galaxies are still fast approaching each other, like they're in a demolition derby. It's a place where planets spin sideways, where a day lasts longer than a year, and where sound is a concept that simply doesn't apply. Today, we are opening the ultimate cosmic suggestion box. We're tackling 12 of the most baffling, brilliant, and bizarre questions about the universe. These are the $1 trillion questions that keep astronomers up at night. Why does the universe seem to break its own rules? Get your brain buckled in. We're about to take a ride through the weirdest paradoxes in space, from the impossibly hot to the impossibly invisible. Why black holes swallow light, but we still see them. First up, the heavyweight champion of cosmic monsters, the black hole. The very definition of a black hole is a region of space-time where gravity is so strong that nothing, not matter, not radiation, not even light itself, can escape. It's the ultimate Hotel California. You can check in, but you can't check out. The boundary of this point of no return in space-time is called the event horizon. So, here's the paradox. If light can't escape, a black hole should be, by definition, the most invisible thing in the universe. It's a literal black hole in space. So, how did we take a picture of one? How do we even know they're there? If we see them, doesn't that break the whole concept? Well, the universe is tricky. We don't see the black hole itself. We see the chaos it creates. We see its mess. Imagine a perfectly invisible, perfectly silent person standing in the middle of a crowded, muddy, noisy food court. You'll never see them, but you will see the chaos they cause. You'll see the ring of people around them screaming. You'll see the "Caution, wet floor" sign as they spill a giant soda. You'll see them grabbing food off people's trays. We see black holes in 4 main ways. Method 1. The messy eater, the accretion disk. A black hole sitting alone in space is indeed invisible. But a black hole that is feeding is the brightest thing in the universe. When gas, dust, and the occasional unlucky star get pulled toward a black hole, they don't just fall straight in. Thanks to the conservation of angular momentum, the same reason an ice skater spins faster when they pull their arms in, this material spirals inward. It forms a massive, flat, spinning plate of superheated material called an accretion disk. This disk is a nightmare of friction. The material closer to the black hole is orbiting at millions of miles per hour, faster than the material farther out. This rubbing and shearing heats the gas up to billions of degrees. When you heat something up, it glows. When you heat something up to billions of degrees, it doesn't just glow, it screams. It blasts out unimaginable amounts of energy, from radio waves to visible light to, most prominently, X-rays. What we see is not the black hole. We see its food, superheated to the point of incandescence, shining brighter than 1 trillion suns just before it takes the final plunge over the event horizon. These are known as quasars, and they are beacons across the cosmos, all powered by the gravitational energy of a black hole having a meal. Method 2. The shadow, the Event Horizon Telescope. This is how we got that famous 2019 photo of M87 Nynx, and the more recent one of Sagittarius AC, the one at the center of our own galaxy. Even with a feeding black hole, you still have the problem of seeing the hole itself. The light from the accretion disk is behind the black hole, in front of it, and all around it. But the black hole's gravity is so extreme that it bends light. This is called gravitational lensing. The black hole acts like a giant, distorted funhouse mirror. It takes the light from the part of the accretion disk behind it and bends it up, over, and around, creating a bright ring. But right in the middle, there is the point of no return. Any light that tries to come from that spot or passes too close to it is captured forever. This creates a shadow. This shadow is the hole in the donut. It is the visual representation of the event horizon itself. It's the ultimate cosmic eclipse, caused not by an object blocking the light, but by space-time itself folding over and trapping the light. Method 3. The bully, gravitational lensing. What if a black hole isn't feeding? What if it's just sitting there, silently? We can still see its effect. Remember, gravity bends space-time. Light must follow the curves of space-time. So, if a black hole, even an invisible one, passes between us and a distant galaxy, the light from that galaxy will be bent around the black hole. We might see the galaxy appear in two places at once. We might see a distant star field suddenly warp and distort. We might see a perfect circle of light, called an Einstein ring, which is the light from a single object behind the black hole, lensed into a halo. We aren't seeing the black hole. We are seeing its gravity acting as a lens. We are seeing the shape of the warped spacetime it creates. Method 4. The dance partner. Stellar orbits. This is how we first confirmed the black hole at the center of our galaxy. For decades, astronomers watched the very center of the Milky Way. They saw a star, called S2, that was absolutely whipping around an empty spot in space. It completes an orbit in just 16 years. At its closest approach, it travels at over 8,000 kilometers per second. That's about 3% the speed of light. For a star to move that fast, it must be orbiting something with an unfathomable amount of mass. By calculating its orbit, astronomers determined that this empty spot it was orbiting contained the mass of 4 million suns, all packed into a space smaller than our solar system. There is nothing we know of, except a supermassive black hole, that can be that massive, that small, and that dark. So, we don't see the black hole. We see the star, it's bullying, forced into a frantic high-speed dance with an invisible partner. In short, black holes are masters of a no-touch policy. They're the ultimate cosmic influence. You don't see them. You see the influence they exert on everything around them. Why time slows down near black holes. Alright, so we've established that black holes are cosmic bullies with extreme gravity. This leads us to our next question, pulled straight from science fiction. Why does time slow down near a black hole, like in the movie Interstellar? On Miller's planet, which was orbiting the black hole Gargantua, 1 hour on the surface was equal to 7 years back on the ship. That's not just Hollywood fantasy, that's a real, predicted phenomenon of our universe. The answer is one of the most elegant and terrifying ideas in physics: general relativity. Over a century ago, Albert Einstein didn't just have a good idea, he rewrote the rules of the universe. Before Einstein, we thought of gravity as a force, an invisible rope pulling things together. Einstein said, no. Gravity is not a force. Gravity is the shape of space and time. He unified the 3 dimensions of space, length, width, depth, and the 1 dimension of time into a single 4-dimensional fabric called space-time. His theory of general relativity states that mass and energy bend this fabric. Imagine a trampoline. You put a bowling ball, like the sun, in the middle. The trampoline fabric sags. Now, if you roll a marble, like Earth, nearby, it doesn't fall toward the bowling ball because of a force. It follows the curve in the fabric. A black hole is not a bowling ball on the trampoline. So, where does time come into this? Time is part of the fabric. When you warp space, you cannot avoid warping time as well. They are linked. For a black hole, the funnel it creates in space-time is a gravity well. The deeper you go into this gravity well, the more space-time is warped. And the more space-time is warped, the slower time flows for you relative to someone far outside the well. This isn't just a theory. It's a proven, measurable fact we deal with every single day. You have a GPS in your phone, right? That GPS relies on a network of satellites orbiting Earth. Those satellites are higher up in Earth's, admittedly shallow, gravity well than we are. Because they are in a weaker gravitational field, their clocks literally run faster than ours on the surface. The difference is tiny, about 38 microseconds, millionths of a second, per day. But if the engineers didn't account for this gravitational time dilation, the GPS system would be off by miles within a single day. We have to program the satellites to constantly correct for the fact that time is moving faster for them than it is for us. Now, take that simple, measurable effect and amplify it by 1 trillion. Earth makes a small dimple in space-time. A black hole creates a chasm. As you approach the event horizon, you are descending deeper and deeper into this chasm. To an observer far away, like your friend back on the spaceship, your clock and your heartbeat, your thoughts, your aging, will appear to slow down. You, on the planet's surface, wouldn't feel anything different. Your clock would seem to tick normally, 1 second, 2 seconds, but the very definition of your second is different. It is a longer, more stretched out in space-time kind of second. When you finally blast off and return to the ship, you will find that you have aged only a few hours, while your friend, who stayed in the faster time of weaker gravity, has aged decades. It's one of the most fundamental rules of the cosmos. The speed of light is constant for all observers. To keep that one rule true, everything else must become flexible. Time and space themselves must warp, bend, and distort to accommodate this. Near a black hole, you are in the slow lane of time. At the event horizon itself, this stretching becomes infinite. To an outside observer, an object falling into a black hole would appear to slow down, get dimmer, and never actually cross the boundary. It would be frozen in time forever, redshifted into oblivion. Why the universe expands, but galaxies collide. This one feels like a total contradiction. We've been told, ever since Edwin Hubble, that the universe is expanding. And not just expanding, it's accelerating. Galaxies are flying away from each other. The space between them is being stretched, like dots on an inflating balloon. So, if everything is flying apart, why is the Andromeda galaxy, M31, currently hurtling towards our Milky Way at 110 kilometers per second? That's 250,000 miles per hour. Andromeda isn't just nearby, it's on a direct collision course. In about 4.5 billion years, our two galaxies will merge in a spectacular, violent, beautiful cosmic dance, forming a new, giant Andromeda galaxy. How can this be? Is the expansion a lie? The answer lies in a cosmic tug-of-war between two fundamental forces: dark energy and gravity. On the expanding team, dark energy. This is the mysterious, unknown something that is causing the acceleration of the universe's expansion. It's a property of space-time itself. The more space-time you have, the more dark energy you get, which creates more space-time. You get the idea. It's a runaway effect. Dark energy operates on the largest scales. It is the dominant force between galaxy clusters. It is pushing the Virgo supercluster away from the Laniakea supercluster. On the colliding team, gravity. Gravity is the force of attraction. Mass attracts mass. On local scales, gravity is much stronger than dark energy. Think of it this way. The universe is a giant, expanding piece of raisin-bread dough, space-time. The raisins are galaxy clusters. The dark energy, the yeast, is making the dough itself expand, pushing the clusters farther apart. But what about inside one of those raisins? Our local group of galaxies. The Milky Way, Andromeda, Triangulum, and a few dozen dwarf galaxies, is one of those raisins. We are a gravitationally bound system. The galaxies within our local group are so close to each other that their mutual gravity easily overpowers the weak, large-scale push of dark energy between them. It's like being on a very long, very fast-moving train, the expanding universe. Two people, Andromeda and the Milky Way, in the same train car, the local group, can absolutely get up and walk toward each other. Their local motion has nothing to do with the fact that the entire train car is hurtling away from the next train car, the Virgo cluster. The expansion of the universe is not happening inside our solar system. The gravity of the Sun easily holds the planets. It's not happening inside our galaxy. The gravity of the galactic center holds the stars, and it's not happening inside our local group. The cosmic speed limit is being broken by space itself, but on a local level, gravity still runs the show. Andromeda and the Milky Way are bound by gravity, and they are falling towards each other. The expansion of the universe only affects things that aren't already held together by a stronger local force. No sound in space. How do astronauts talk? In space, no one can hear you scream. It's one of the most famous taglines in movie history, and it is 100% scientifically accurate. But it does raise a good question. If space is a silent vacuum, how do astronauts talk to each other? How does Mission Control talk to the International Space Station? The answer is the difference between two very different types of waves: mechanical waves and electromagnetic waves. Sound is a mechanical wave. What does that mean? It means sound needs a medium. It needs stuff to travel through. When I speak, my vocal cords vibrate. Those vibrations push on the air molecules in front of them. Those molecules push on the molecules next to them, which push on the molecules next to them, creating a chain reaction, a compression wave of molecules that travels through the air. This wave eventually hits your eardrum, vibrates it, and your brain translates that vibration back into sound. Sound can travel through air, water, or even a solid piece of steel. But it must have a medium. Space is a vacuum. It's mostly empty. There are some stray atoms, but they are so far apart that they can't create a compression wave. If you were to float outside the ISS without a helmet and scream, you would vibrate your own vocal cords, but that vibration would have nothing to push against. No medium, no wave, no sound. So, how do astronauts get around this? They don't use sound. They use radio, which is an electromagnetic wave. Electromagnetic waves, like visible light, X-rays, microwaves, and radio waves, are completely different. They do not need a medium. They are self-propagating waves of energy, and they are perfectly happy traveling through a vacuum. In fact, they travel fastest in a vacuum, at the speed of light, because they are light. Here's the step-by-step. 1. The astronaut inside her helmet speaks. The helmet is full of air, a medium. 2. A microphone in her helmet picks up the sound waves, mechanical, traveling through that air. 3. The microphone turns the sound waves into an electrical signal. 4. A transmitter in her spacesuit takes that electrical signal and modulates it onto a radio wave, electromagnetic. 5. This radio wave zips through the vacuum of space at the speed of light. 6. The wave hits the other astronaut's spacesuit. 7. A receiver in that suit captures the radio wave and turns it back into an electrical signal. 8. A speaker in the second astronaut's helmet uses that signal to vibrate, creating new sound waves, mechanical, inside their helmet. 9. The second astronaut hears the first astronaut's voice. So they aren't talking through space. They are transmitting data through space, which is then reassembled back into sound on the other side. And what about inside the ISS? Well, the ISS is full of pressurized air. It is not silent, In fact, it's very loud. Astronauts report that with all the fans, pumps, and life support systems constantly running, it sounds like you're in a noisy office building or a factory, 24/7. Why the moon? Always shows us the same face. Have you ever looked up at the moon and thought, "Hey, you look familiar"? You're right. You have never seen the other side of the moon. Not with your naked eye, anyway. Ever. The moon is locked in a perfectly synchronized dance with the Earth, forever showing us only one face. This leads to a common misconception that the moon doesn't rotate. It absolutely rotates. If the moon didn't rotate, we would see its other side. Think about it. If the moon just sat there, frozen, as it orbited the Earth, we'd see its front, then its side, then its back, then its other side, as it made its way around us. The reason we only see one face is because the moon rotates on its axis at the exact same speed that it revolves around the Earth. This is called synchronous rotation, or more commonly, tidal locking. The moon's day, one full rotation, and the moon's year, one full orbit of Earth, are the same length, about 27.3 Earth days. But why? This can't be a coincidence. It's not. The Earth forced the moon to do this over billions of years, using the power of gravity and tides. Here's how it happened. Billions of years ago, the moon was young, much closer to Earth and spinning much, much faster. Maybe its day was only a few hours long. Now, the moon is not a perfect sphere. It has slight bulges and imperfections. Earth's immense gravity pulled on these imperfections. Just as the moon's gravity pulls on Earth's oceans, creating our ocean tides, the Earth's gravity pulled on the moon's solid rock. Back when it was younger and more molten, this was even easier, creating rock tides, or tidal bulges. The moon was trying to spin rapidly, but the Earth's gravity was holding on to these bulges. This created a massive amount of friction. Imagine trying to spin a lopsided, squishy-ish ball in your hand, while your other hand is gently squeezing it. That squeeze, Earth's gravity, is going to act as a brake, slowing the spin down. Over millions and millions of years, Earth's gravity acted as a relentless brake on the moon's rotation. It slowed and slowed and slowed until it reached what we call the lowest energy state. This is the most stable configuration. That state was achieved when the moon's rotation matched its orbit. At this point, the bulge, the moon's heaviest side, was permanently facing the Earth. The brake was no longer needed because the part Earth wanted to pull on was already facing it. The system became locked. It's like spinning a coin. It spins and wobbles, fast rotation. But eventually, it slows down and settles flat on the table, the lowest energy, locked state. So, the moon is rotating. We just happen to be in the front row seat of its 27.3-day orbit, so its rotation perfectly masks its dark side, which should really be called the far side, since it gets just as much sunlight as the side we see. Why shooting stars burn up. We see them all the time, especially on clear summer nights. A bright streak of light flashes across the sky. A shooting star. Make a wish. It's a beautiful sight. But what is it really? First, it has nothing to do with stars. Stars are giant balls of nuclear fusion, millions of light years away. A shooting star, or meteor, is a tiny piece of rock or dust, often no bigger than a grain of sand or a small pebble, hitting the Earth's atmosphere at insane speeds. These bits of debris are called meteoroids when they are floating in space. They are the leftovers from the formation of the solar system, or, more often, the dusty trails left behind by comets. As Earth orbits the Sun, we are a giant vacuum cleaner, plowing through these clouds of space dust. The speed is the key. Earth is traveling at about 67,000 miles per hour, 30 km/s. The meteoroid might be traveling just as fast in the other direction. When they meet, the closing speed can be over 150,000 miles per hour, 70 km/s. Now, here's the common misconception. We say they burn up due to friction. That's sort of true, but it's not the main reason. The real culprit is not friction, it's compression. This is called ram pressure. When the meteoroid hits our atmosphere at this hypersonic speed, it doesn't have time to push the air molecules out of the way. It compresses the air in front of it violently. When you compress a gas, it gets hot. Really hot? You know this if you've ever used a bicycle pump. The pump gets hot as you compress the air. Now, imagine compressing the air so fast that it has no time to escape. The air in front of that tiny pebble is compressed so much, so instantly that it heats up to thousands of degrees. It becomes a plasma, a superheated, glowing gas. What we are seeing is not the pebble burning. We are seeing the air itself, being flash heated to incandescence by the shockwave of the meteoroid's passage. This intense heat, this plasma sheath, is what then vaporizes the pebble. The pebble, or grain of sand, is ablated. It turns directly from a solid into a gas, leaving that fiery streak behind it. The streak of light we see is the trail of superheated air and vaporized rock atoms glowing in the upper atmosphere, usually about 50 to 75 miles above our heads. So, a shooting star isn't a thing. It's an event. It's the final, fiery, spectacular death of a tiny piece of cosmic dust, all thanks to the physics of extreme air compression. Why Venus is hotter than Mercury. This one just doesn't seem fair. Mercury is the closest planet to the Sun. It is the front row seat to a star. At its closest, it's only 29 million miles from the Sun's blistering surface. Venus is second. It's, on average, twice as far from the Sun as Mercury is. So Mercury must be the hottest planet, right? Wrong. Mercury is complicated. But Venus is hell. Let's look at the stats. Mercury, daytime, 430 C, 800 F. Very, very hot. Mercury, nighttime, 180 C, 219 F. Colder than Antarctica. Venus, all the time, 460 C, 870 F. Venus is hotter than Mercury all the time, day and night, at the poles and at the equator, despite being twice as far from the Sun. How? The difference is one word: atmosphere. Mercury is what you call a nudist planet. It has no clothes. It is, for all intents and purposes, an airless rock. This means that during the day, the Sun blasts its surface, heating it to incredible temperatures. But because there is no atmosphere, no blanket to hold that heat in, the instant the Sun goes down, which takes a while as its day is 59 Earth days long, all of that heat radiates straight back out into space. Mercury cannot retain heat. It's a classic boom and bust temperature cycle. Venus is the exact opposite. Venus is not wearing a blanket, it is wearing a pressure cooker. Venus has an atmosphere. Oh, does it have an atmosphere? It is an insane, runaway atmosphere. 1. It's thick. The atmospheric pressure on the surface of Venus is 92 times that of Earth. 2. It's toxic. The atmosphere is 96.5% carbon dioxide, CO2, and that CO2 is the key. This is the runaway greenhouse effect. Here's how it works. Sunlight, which is high-energy visible light, comes from the Sun and travels through Venus's thick, cloudy atmosphere. It hits the ground and heats up the surface of the planet. The hot ground then tries to cool off by radiating that heat back, but in a different form. Low-energy infrared radiation, heat. But that massive 96.5% CO2 atmosphere is transparent to visible light coming in, but opaque to infrared heat going out. The CO2 molecules absorb the outgoing heat, trap it, and radiate it back down to the surface. The heat cannot escape. It's like sitting in a car on a sunny day. The sunlight comes through the glass, visible light, heats the dashboard, and the dashboard radiates heat, infrared. But the heat can't get back out through the glass very well. The car gets hotter and hotter. Now imagine that car's atmosphere is 90 times thicker and made almost entirely of the glass itself. Venus is a runaway case because billions of years ago, it may have had oceans. But as it got warmer, the oceans boiled. This put more water vapor, another greenhouse gas, into the air, which made it hotter, which boiled more oceans. This cycle fed on itself until the planet became a sterile, lead-melting thermal nightmare. So, Mercury gets more raw heat from the Sun, but it can't keep any of it. Venus gets less heat, but it has trapped almost every bit of energy it has received for billions of years. Why Mars has a red color. We call it the red planet. We see it in the night sky as a distinct reddish-orange point of light. Our rovers send back images of a seemingly endless, dusty, rusty red landscape. But why? What makes it so red? The short, simple answer is that Mars is rusty. The long answer is a bit more interesting. The official name for rust is iron oxide. It's what happens when iron atoms react with oxygen. The surface of Mars, the rocks, the soil, the regolith, is extremely rich in iron. This is true for most of the rocky planets, including Earth. Iron is a very common, heavy element forged in the hearts of ancient stars. On Earth, most of our iron is locked up in the planet's core. Mars, being smaller, may not have differentiated as completely, leaving more iron spread through its crust. But iron itself is not red. A piece of pure, unoxidized iron is a dark, silvery gray. To get red rust, you need the second ingredient, oxygen. Today, Mars's atmosphere is 95% CO2 and paper-thin. There is almost no free oxygen. So, where did the oxygen come from to rust an entire planet? This is the mystery. We are looking at the ghost of a different Mars. Billions of years ago, Mars was a very different place. It was warmer, it had a thicker atmosphere, and, most importantly, it had liquid water. We see the evidence everywhere: dried-up river deltas, ancient lake beds, minerals that only form in water. So, here's the theory of the Great Rusting. In Mars's ancient past, that liquid water, H2O, was all over the surface. At the same time, the thicker atmosphere was being battered by solar radiation. The sun's ultraviolet light would hit water molecules, H2O, in the atmosphere and split them apart. This is called photodissociation. H2O would split into hydrogen, which is very light and escaped to space, and oxygen, which is heavier and stuck around. This newly freed oxygen was highly reactive. It attacked the iron-rich rocks on the surface. Over millions and millions of years, this oxygen weathered the surface, bonding with the iron to create iron oxide. Rust. This process essentially rusted the entire surface of the planet. Today, Mars is covered in a fine dust of this iron oxide. It's a rusty, talcum powder-like dust that covers everything. This dust is so fine and the gravity is so weak that it gets kicked up into the thin atmosphere by winds, creating giant, planet-circling dust storms. This dust in the atmosphere is also what gives the sky on Mars its eerie, pinkish-red color. So, when you look at Mars, you are not just seeing a red planet. You are seeing the ancient chemical scar of a world that lost its water and, in the process, rusted over. Why Saturn could float on water. This is one of hidden facts you hear in elementary school, and it sounds insane. If you had a bathtub big enough to hold Saturn, Saturn would float. Is that true? Is it a metaphor? No, it is literally true. This has nothing to do with weight. Saturn is the second most massive planet in the solar system. It weighs 95 times more than Earth. If you put Saturn in a giant cosmic bathtub, it would be an incredibly heavy, massive object. But floating has nothing to do with weight. It has to do with density. Density is the mass per unit volume. It's not how much you weigh, it's how much stuff is packed into how much space. A 1-ton block of steel is very dense. It sinks in water. A 100,000-ton aircraft carrier, which is made of steel, is on average less dense because most of its volume is empty air, so it floats. The ruler we use for density is water. We define the density of pure water as 1 gram per cubic centimeter, 1.8 text G cm $3. Anything more dense than 1 as text G cm $3, like a rock or steel, will sink. Anything less dense than $1 or text G in cm $3, like wood or ice, will float. So the question is, what is Saturn's average density? Saturn is a gas giant. It is not a rocky planet, it is a colossal ball of gas. It might have a small, rocky, icy core, but the vast majority of the planet is simply gas. And what gas? Hydrogen and helium, the two lightest and least dense elements in the entire universe. While the pressure deep inside Saturn is immense, compressing this hydrogen into a liquid and even a metallic state, the average density of the entire planet, all that mass divided by all that volume, is 0.687 G ECM-3. Saturn's average density is less than water's. It is the only planet in our solar system that is less dense than water. So, yes, if you could build a cosmic bathtub trillions of miles wide, and if you could find enough water to fill it, which is another problem, and if you could move Saturn without it tearing itself apart, it would absolutely bob on the surface like a giant, ringed, beige-colored beach ball. Of course, in reality, the water would freeze, the planet's gases would interact with the water, and the whole thing would be a catastrophic mess, but the physics is 100% sound. Why Uranus is tilted 98 degrees. The solar system is a pretty orderly place. The Sun spins, and all the planets orbit the Sun in roughly the same flat disk, the ecliptic plane. And most of the planets spin in the same direction, with their north pole pointing up, more or less. Earth is tilted at 23.5 degrees. This is normal. It gives us our seasons. Mars is tilted 25 degrees, Jupiter 3 degrees, and then there's Uranus. Uranus is the oddball, the rebel, the what is wrong with you planet. Uranus's axis of rotation is tilted 98 degrees. It's not tilted, it's knocked over. It is not spinning like a top as it orbits the Sun. It is rolling like a barrel. This has bizarre consequences. Because it is on its side, its 84-year orbit around the Sun is extreme. For 21 years, its north pole is pointed directly at the Sun. This is one long 21-year summer day. Then, as it continues its orbit, the Sun sets. It then spends 21 years with its equator facing the Sun, giving it a 42-hour day-night cycle. Then, its south pole points directly at the Sun for a 21-year winter day for the other hemisphere. It is a world of the most extreme seasons imaginable. So, the obvious question is, what happened? Why is one planet so completely messed up, while the others are mostly normal? The answer, as with most violence in the solar system, is it got hit. We are 99.9% certain that this is the answer. Billions of years ago, when the solar system was young, it was a violent place. It was a cosmic pinball machine of planetesimals, protoplanets, and giant boulders the size of moons, all crashing into each other. This is how we think our own moon was formed. A Mars-sized object named Theia slammed into the early Earth. The only working theory for Uranus's tilt is that during this chaotic period, Uranus was struck by a massive object. We're talking something the size of Earth, or perhaps two smaller objects in quick succession. This great impactor didn't just nudge Uranus, it collided with such cataclysmic force that it knocked the entire planet over onto its side. And the evidence is right there. Uranus's rings and its moons are also on this 98-degree tilt. They orbit Uranus's sideways equator. This strongly suggests that they formed from the debris of this ancient, world-shattering collision. The impact was so great it blew a cloud of rock, ice, and gas into orbit around the new, sideways Uranus, and that cloud eventually coalesced into the rings and moons we see today. Uranus isn't just tilted, it is the scar of one of the most violent collisions in our solar system's history. Why a day on Venus is longer than a year. We're back to Venus. We've already established it's a hellscape, but its weirdness is just getting started. Let's define our terms. A year is the time it takes a planet to orbit the Sun. A day is the time it takes a planet to rotate once on its axis. On Earth, year, 365 days. Day, 24 hours, easy. On Venus, it's year, 1 orbit. 225 Earth days. It's day, 1 rotation. 243. Earth days. Wait, you read that right. It finishes its orbit around the Sun before it has finished spinning once. A single day on Venus is longer than its entire year. If you were standing on Venus, which you can't be, you'd be dead. The Sun would rise. You would celebrate your birthday, and the Sun would still be in the sky. And, to make it even weirder, it spins backwards. On Earth, the Sun rises in the east and sets in the west. On Venus, the Sun rises in the west and sets in the east. This is called retrograde rotation. What happened to this planet? This is one of the biggest unanswered questions in planetary science, but we have 2 very good theories. Theory 1. The big hit, again. Just like with Uranus, one very good way to mess up a planet's rotation is to smash it with something huge. It's possible that billions of years ago, a massive planet-sized object slammed into Venus. But instead of knocking it over, like Uranus, it hit it in a way that killed its spin, and even reversed it. The impact would have stolen all of its angular momentum, spinning it down to the crawl we see today, and in the wrong direction. Theory 2. The thick atmosphere, the cooler theory. This one is more subtle and, in my opinion, more terrifying. What if Venus did this to itself? Venus's atmosphere is so thick, 90 times Earth's pressure. It is a soupy, heavy ocean of gas. This thick atmosphere is also being pulled on by the Sun's gravity, creating atmospheric tides. This is like the ocean tides on Earth, but with the air. This creates a colossal amount of friction. We're talking about a planet trying to spin, while its own 90 times thicker than Earth's atmosphere is sloshing around it, dragging against the surface and being tugged on by the Sun. The leading non-impact theory is that this atmospheric drag, this tidal friction from its own atmosphere, has acted as a brake for billions of years. It's possible Venus used to spin normally, like Earth. But over eons, its own runaway greenhouse atmosphere slowed its rotation down, and down, and down, until it stopped, and the complex dynamics between the Sun's gravity and the sloshing, heavy atmosphere actually pushed it slightly backward, resulting in the slow, retrograde crawl we see today. Either way, Venus is a lesson. It's what happens when a planet goes terribly, terribly wrong. Why galaxies have beautiful spiral arms. Finally, let's zoom all the way out. When you think of a galaxy, you almost certainly picture it. A beautiful, majestic, swirling pinwheel of stars. Bright arms filled with gas and light, curling out from a dense, bright center. Our own Milky Way is a spiral galaxy. Andromeda is a spiral galaxy. They are the poster child of the cosmos. But why? Why that shape? Why aren't galaxies just blobs? Some are blobs. They're called elliptical galaxies, but we're talking about the spirals. If the whole galaxy is spinning, why don't the arms just wind up? If you imagine the arms as being physically attached to the stars, like ropes, the center of the galaxy, which spins faster, would wind them up tight in just a few 100 million years, smearing the spiral into a blur. But we see these open arms everywhere. This means the arms are not a thing. A spiral arm is not a rope, it's a wave. The answer is density wave theory. This is, by far, one of the coolest concepts in astrophysics. Imagine a traffic jam. The traffic jam itself, the slowdown, moves along the freeway. But the cars in the jam are not the same cars. Cars approach the jam, slow down, move through the jam, and then speed up and leave it. The spiral arms are traffic jams for stars. Here's how it works. 1. The disk. A galaxy like ours starts as a giant, rotating cloud of gas and dark matter. As it collapses, it flattens into a disk, like a spinning pizza dough. 2. The stars. All the stars and gas clouds in this disk are orbiting the central core, but they don't all orbit at the same speed, the winding problem. 3. The wave. For complex reasons, maybe a bar in the center or a near collision with another galaxy, a pattern emerges. This pattern is a wave of higher gravity, a density wave that sweeps through the disk. 4. The jam. This density wave moves through the disk at its own speed, which is different from the speed of the stars. So here's what happens. A star, orbiting peacefully, approaches one of these density waves, a spiral arm. As it enters the arm, the gravity is higher. This squeezes the star's orbit and causes it to slow down. It's entering the traffic jam. It spends a few million years inside the arm, bunched up with other stars. Then it passes through the arm, and on the other side, it speeds up again, continuing its lonely orbit in the empty space between the arms. The stars move through the arms. The arms are just the place where the stars bunch up. But why are the arms so bright? This is the beautiful part. Stars just bunch up. But gas clouds, the giant nebulae where stars are born, do something different. When a giant gas cloud hits this density wave, it gets squeezed. What happens when you squeeze a gas cloud? You trigger star birth. The instant the gas hits the traffic jam, it collapses and ignites into thousands of new, hot blue stars. These new stars are incredibly bright, but they are also very short-lived. So, the reason the spiral arms are so bright and blue is not because that's where all the stars are. It's because that's where all the newborn stars are. The spiral arm is a stellar nursery. It is a wave of creation sweeping through the galaxy. By the time those bright blue stars get out of the arm, they've already died. A spiral arm is a pattern. It is the visible trace of a gravitational shock wave that is constantly triggering new star formation. It is the universe's most beautiful, large-scale traffic jam. And exhale. From the time-bending gravity of a black hole, to the atmospheric brake pedal on Venus, to the cosmic rust on Mars, the universe is so much weirder and more wonderful than we can imagine. The rules we think are common sense simply don't apply. The cosmos is a chaotic, beautiful, and paradoxical place. And the more questions we answer, the more fantastic, mind-blowing questions we find. Thank you for joining us on this tour of the cosmic why. If you have more questions that are bending your brain, drop them in the comments below. Until next time, this is NK Fantastic, reminding you to stay curious.